right? But today in our topic of discussion would be mostly based on the conformation analysis of the cyclic system. We already know about the acyclic system, right? So I don't want to go into that detail. You already, I will go through some of the examples which will clarify that what the ace conformation of acyclic system is about. But I don't want to take much of my time in explaining the conformational analysis of the acyclic system, because in a course content we are bound to explain the conformation analysis of the cyclic system. Okay, first of all, what is the main difference between the configuration and the conformation? I don't understand that I need to tell you about that, because during our very first or the second lecture we talked too much about the configuration and the conformation analysis. You know, configuration is something that whenever we bring about a change in the structure of the molecule, I mean all the type of the you see that whenever you are studying about the stereochemistry, there are two type of the subtypes we have studied about the stereochemistry. One was the configuration, the other was the conformation. In configuration, somewhere you are dealing with the, for instance, you are talking with the talking about the double bond cis and trans isomers. So these are the configurational isomers. More precisely, they are geometrical isomers, right? Because you see that their structure, they are different. The structure is different, right? What kind of they are different in the three-dimensional space, but in the conformation we see that the molecule remains the same, but one part of the molecule start moving with respect to the other. So this is the main difference. Configurations, as I said, there are two types of the stereoisomer configuration conformation. In the configuration, you said that there are geometrical or the optical isomers, right? So stereo, let me again remind you that thing that we have shared at the very first day, that the stereochemistry was basically, the stereochemistry was divided into two subtypes, right? Sorry that I'm not quite feeling convenient with using this apout software. So we have discussed about the two types of the subtypes of the stereo chemistry. One was the configuration and the other was the conformation. This was about the configuration and the other was the this is configuration and conformation. In the conformation also we have discussed about the various type of the, I mean this configuration and the then we have discussed about the geometricals, the cis-trans isomers, and then the optical isomers, geometrical and optical isomers. And then we have also discussed about the conformation. So in configuration, whether that is configuration and conformation, they are all stereo isomers. They are different in the three-dimensional space, but in configuration, as I said, that if we talk about the like the cis-trans isomer, the structure they are different. For instance, you are taking the firstly the cis and then the trans. So there is a change in the configuration somewhere in the molecule, right? This configuration, you see that for instance is C methyl, here is a methyl, here is H, right? And here is again methyl and here is H, right? So you see that these two, this is the cis, and on the trans you see there are two substituent will be on the opposite sides. So if we move back and look, The three-dimensional space here in the space, the one side for in the case of the trans, we found that there are different substituent altogether on a distant side. For instance, with trans we have this kind of the situation. Methyl would be here, right, and the other methyl would be here, and here this will be H. And you can see that here this side we are facing, methyl is facing the hydrogen, but on this side methyl is facing the methyl. So this has a completely different 3D structures, right? The proximi are the nearest groups, they are different, right? In the conformation we see that the molecule is rotating around the single bond, just like this example. One part of the molecule rotate with respect to the other. In configuration, we saw that there is no free rotations in case of the cis-trans isomer. Just don't forget that configuration is not only restricted to this geometrical isomers. The optical isomer could also be the configurational isomer. I mean, they could also be, could be a different conformation. Whenever you're talking about the single bond, you see that in a single bond, you draw the various structure of the sugar. In that sugar, somewhere you differ the substituent. For instance, this is CHO, right? It says CHO. Here there's a H, right? Here there's a OH group, right? Here is a H, right? Here again any OH or maybe something different, and here is a CH2OH. So for instance, if I am going to bring about the change in the conformation, change in the configuration at only one position. For instance, I am replacing this, I'm just changing this H, right? Changing the configuration at only one side. I mean, I'm shifting this H to here and this OH to here. So there will be a change in configuration at only one stereocenter. So this will not make this as a, I mean, the enantiomer of the other. There is a single change in the configuration at only one side. That means that the previous one is the configurational isomer to the new one, because there is a single change in configuration. So this is also a configurational isomer. There is no double bond in it. So configurational isomers are not only the geometrical isomers, that they will be the configurational isomer, and they always need to have the double bond. It's not necessary. Even they could be there could be a configurational isomer whenever we have when we are dealing with a single bond, such as this one. In the whole, if there are more than one stereocenter, and if there is a change in configuration at only one center, the previous one will be the configurational isomer to the new one. So this is how they are. But on the other side, if you talk about so in configuration, we see that there's a structural change. But remember, they are not the constitutional isomer. So if we bring about the change in the structure, that means that we are going toward the constitutional isomer. They are not the constitutional isomer. Structural change is only because in the three-dimensional space, you have this restriction. Whenever you are dealing with the configurational isomer, the change in structure would be only permissible, the one where there is a single change in the configuration in a three-dimensional space. Without in a constitutional isomer, what you were doing, you are detaching one of the group from one side, and then you are placing it on the other side. That was the constitutional isomer. But in the configurational isomer, we are not going to do that. We are not detaching any substituent from anywhere else and placing that on the other side in the molecule. If you do that, that will be a constitutional isomer. Right? So you understand. Let me explain it in the other video.